So hello everyone, my name is Dina Zhabinskaya and I will be your instructor for Physics 7C this quarter. So I know that this is a very strange quarter for all of us, both for instructors and students. You know, right now I'm sitting in my home office looking at my computer screen, so it feels very strange to be talking this way rather than to an audience of wide awake and eager students at 7:30 in the morning on Thursday. And I'm sure for you as well, it's strange to not be able to talk to your peers and friends and your TAs and instructors in person in order to help yourself through the quarter. But hopefully we're gonna get used to it, and we're just taking the necessary precautions in order to stop the spread of the COVID-19 virus, in order to protect our health and the health of our loved ones. So this is what we have to do. However, I'm optimistic. We have an amazing team of instructors and TAs working really hard together to make sure that you have the best educational experience that we can provide you given these unusual circumstances. So before I move on into physics, I just want to point out some of the resources that you should be using this quarter. I mean, in general, make sure that you read the syllabus of the course, as it's quite different from the regular quarters, which was changed in order to fit the online structure of the course. And as far as the resources, so the first one mentioned here are some DL videos that one of our TAs, an amazing TA Patrick, he's making them mostly to supplement some activities that need to be done in person in DLs, various measurements and so on that you would have done in 7C, and also to give you a brief overview of summary of each DL, since we realize that learning in an online DL structure might not be optimal. Then there's the online lectures here, which are just basically lectures taped by, given by another professor a couple of years back, just if you want to get another perspective of this material being introduced. Then there's the online textbook for 7C. And in addition, I know a lot of you enjoyed this channel in 7B called the Physics Angels. The TA who is making it is also making some 7C videos for you this quarter, which basically focus on kind of leading you through the problem solving for some practice quizzes and problems and so on. All right, so for most of you probably already had your first DL by the time you watch this video, and you've noticed that we start with wave phenomena. And it starts a little bit abstractly, kind of understanding what is a wave, how do we describe it, but throughout this entire quarter, you will see a lot of applications to waves. So we're gonna look at things like optics, how mirrors and lenses work. Then we will talk about what we'll feel is very different, electricity and magnitude, but as we will see later, it's all still connected to electromagnetism, which is light described by wave phenomena. All right, so what exactly is a wave? Well, a wave is not necessarily something physical, rather it's a disturbance or energy that propagates through matter. So what is that matter? So for example, if we're talking about sound waves, they travel through air. Water waves travel through water, so the medium is the water particles, and there's other types of mediums through which you can create waves, such as slinkies or strings. You'll see a little simulation in DL where you look at a wave on a string. And then, as I mentioned, we will talk about light waves. Light waves are quite different from these other waves because, unlike the other waves, they do not need a medium. We know that the universe is very large and there's a lot of empty space, so there's nothing physical there, because, you know, here, like for sound waves and water waves, we're talking, the reason why these waves can propagate is because in the air, there's air molecules, in the water, there are water molecules, and so on. But in the universe, there's nothing, yet light can still propagate because, you know, we know that the light from the sun comes to the earth to keep us warm. Okay, so how do we describe a wave? Waves have different characteristics or features, so I will talk a lot about these today, such as the amplitude, speed, frequency, wavelength, and polarization. So I'll start with polarization, and polarization basically describes how the wave propagates. So for example, in the top picture, this is known as transverse wave. So the wave is moving either right or left, as this person is kind of moving it up and down. But the wave itself, or the particles in the medium, oscillate up and down here. Where a longitudinal wave, as shown here, the oscillations or the motion of the individual kind of particles within the medium are in the same direction as the motion of the wave. So for example, sound waves are longitudinal, but water waves or waves on a string are transverse. So there are two kind of important things to keep in mind when we're talking about waves. And one is the medium through which the wave is traveling, as I just discussed, such as air or water. And what the medium determines is the speed of that wave. So it's the actual physical properties of the medium itself that determine the wave speed. For example, sound has a different speed in air versus water because the two are different mediums. Now the source is what is creating that wave. So what causes sound wave is, for example, my voice. So my voice is the source. What causes a water wave? So if we're thinking about ripples in a pond, what could be causing it? Let's say you're throwing some stones into the pond, causing that wave. Or with a slinky or rope, it's your hand that's moving up and down. So that would determine the source. And the period, which I will describe in great detail shortly, which defines how fast, in a sense, this wave is oscillating up and down, that's determined by the source. So for example, how frequently are you throwing rocks into the pond, or how frequently are you moving your hand up and down to create the oscillation in the rope? With sound, the period is related to the pitch of the sound. Also, what we will see, another property is the wavelength, and what we'll see shortly is it kind of depends both on the medium and the source, because the way the speed of the wave is determined as the wavelength over the period. So the speed is a medium-dependent quantity, period is a source-dependent quantity, so wavelength depends on both. So how exactly do we sort of model a wave? So imagine, you know, in physics, as you probably already seen from 7A and 7B, we like to simplify things and build models. And now what I'm gonna spend the next couple of minutes talking about is how exactly do we model a wave. So the way we do that is we imagine our medium, something like this, as composed by a bunch of what we call oscillators, so particles in the medium. Again, these could represent air particles if we're talking about sound waves, or water particles if we're talking about water waves. And another thing, what we model is we imagine that they're connected by some kind of springs, which allows them to interact. Now, when there's a periodic disturbance So a wave is something that has this periodicity, so it has to be a periodic disturbance is introduced to this medium, then each particle in the medium oscillates in a wave-like manner, which looks a lot like a sine function. So we will see that these waves can be described mathematically with sine functions. So how do we describe one period in an oscillation? So what this plot represents is just an oscillation of one particular oscillator, like this green dot in this medium, over one period. So if we say that at some time equals to 0, this particle is at position, what we defined y equals to 0, which is its equilibrium position. Equilibrium meaning is when the medium is not being disturbed, that's where it is. As this wave propagates through this medium, then this oscillator, if you imagine this being a transverse wave, would kind of move up and down as this disturbance goes through the medium. So this motion of up and down as a function of time is represented here, where, well, in this case, it's showing this oscillator first going down, and then going back up and returning back to its equilibrium. So when it's back to its starting position, that's what defines one cycle, and the time that it takes for that cycle is exactly known as the period. Another value you see here is this A, which is known as the amplitude of the wave, and that's basically defined as the maximum displacement from equilibrium. So when this oscillator goes up, it goes up by a maximum value of plus A. When it goes down by a maximum value of minus A. So that's how one particular oscillator behaves, but then the medium as a whole has in space this wave-like structure as well. So if we look now not just at the green dot, but all of the dots together in space, then they will have at some instant in time a structure like this, which changes with time as this wave is moving through space. So that's why you see here these different colors representing the positions of these different oscillators at a given instant in time. Now, the period, kind of the spatial period here, when you have one oscillator, the red one, being at its maximum displacement, and then this one over here, this kind of turquoise color, they're at the same displacement from equilibrium, which in this case is the maximum, then the distance between these two is exactly defined by one wavelength. So you could think of a wavelength as sort of the spatial period of the wave. All right, so what we want to do next is describe mathematically this wave. So first we will just again focus on one oscillator, this green one, which is located at a given position in space, and try to think about how do we describe mathematically its displacement. And whenever I say displacement, it just means distance from equilibrium as a function of time. So as we saw this picture previously, it looks a lot like a sine function. So indeed, it is described by a sine function, as you see here. So let's now try to understand all these different features of this sine function. So this value A, that's a constant for a particular wave, and that's is known as the amplitude. The amplitude depends on the amount of energy that you're transferring to the wave. So for example, if you're creating a wave on a rope, it's sort of how much are you moving that rope up and down to give that amplitude. If you're creating ripples in a pond, it's sort of with what speed are you throwing the rocks into the pond, which will create a larger displacement of the water. So it's, again, amplitude is something that depends on the source of the wave. The period, again, has to do with the source because it's how frequently are you disturbing that medium. So how frequently are you moving your hand up and down to create the wave? So this goes here, and we will see very shortly why it has this structure, because we're going to use kind of radians to describe cycles here. So that's why there's that factor of 2 pi. And then this phi naught we'll explain shortly too. That just has to do with your initial conditions. So what do you define as your time equals to 0? All right, so let's kind of see how each variable changes the way this function behaves. So you could see here, t is your variable. This is how this y, which is this displacement from equilibrium, is changing as a function of time, t, where all these other things like a, capital T, and phi naught are constants for a particular wave. All right, so let's look at the amplitude. So here I draw a bunch of sine functions with various amplitudes. So the larger the a, the larger is the maximum displacement. So the blue sine function here has a displacement of 5 here. It should have units of space. It could be centimeters of meters, where the green one is the smallest displacement, which is 1. Now the period, again, that defines how much time does it take to complete one cycle. So for example, the green plot here, one cycle again represents you start at equilibrium, you go up, you go back down, and you return back to equilibrium. That's one cycle, so it's 8 seconds. The blue one has a shorter period, which is only 2 seconds. So another very useful quantity to describe the kind of the temporal periodicity of a wave is known as frequency, and we will use these two quantities interchangeable all the time depending on which one is convenient to think about. So the difference between period and frequency is they're inversely proportional to each other. So if period has units of time, the frequency has units of 1 over time. And the most common unit of frequency is hertz, which is 1 over second. So basically what the frequency tells you is the number of cycles per unit time. So we can see here, for example, the green one, let's focus on the red one. So in 1 second, it goes up and back down. So this is exactly half of the cycle. So it's half a cycle per second. So the frequency will be 1 over 2, which is exactly 1 over the period. Now for the green one in 1 second, it only goes, so going all the way up is 1/4 of a cycle, and it goes half of that. So that's 1/8 of a cycle. So in 1 second, it's 1/8, 1 over 8 seconds, 1 over 8 hertz. All right. So what is this phi naught? All that really does to the sine function is shift it. So what it tells you is where is the displacement at whatever you define as time equals to 0. So when you have a sine function like that, we know that sine of, so when time is 0, and if phi naught is 0, then the sine of 0 has to give you 0. So that's this situation right here. But what about if you had your displacement as a function of time behaving this way? So instead of going to a maximum in the beginning, your oscillator is going to a minimum. So there are 2 ways that you can make sine 0. It's either when everything inside here is 0, or sine of pi is also 0. So how do we know which one to choose? Well, when we put pi here, what it does, it shifts the whole sine function by half a cycle. So if we look at kind of our original sine function, adding pi here, what it does, it basically shifts your axis by half a cycle. So 1 cycle represents 2 pi, half a cycle is 1 pi. So it's as if instead of starting right here, we're starting right here, which is exactly what the sine function shows. All right, so here's another example. Imagine that at time equals to 0, your oscillator started at a maximum. So what is that? That's taking your sine function and shifting it by not half a cycle, but a quarter of a cycle, which is pi over 2. So we know that sine of pi over 2 is 1, and that's going to be your maximum. So in this case, then phi naught, which is called, by the way, the phase constant of your wave, is going to be pi over 2. Now, an interesting feature of sine functions is that you can add any factor of 2 pi to the sine function, and you get the same answer. So whether we're talking about shifting it by a quarter of a cycle or an entire cycle yet in another quarter, we would end up with the same exact looking sine function. So phi naught being pi over 2 or 5 pi over 2, which is basically just pi over 2 plus 2 pi, those are identical. So they're basically kind of an infinite number of identical values for phi naught. Although mathematically, to make your function look nice, you normally choose one which is closest to 0. So pi over 2 is a little bit nicer looking than 5 pi over 2. All right, so here's our last example. Imagine we started at a minimum and then it went up. So that's like taking your axis and shifting it by half a cycle and then another quarter, which is 1.5 or 3 pi over 2. So 1.5 of pi. And we know that sine of 3 pi over 2, which is right here, is minus 1. So that's why we started at the minus. Here it's 2 because A is 2. All right, so typically if this was a real lecture, I would ask you a clicker question. Well, the good thing about watching a video is that, you know, you can pause, think about it. And then, so I encourage you before you go to the next part of the video to kind of pause and think about this. And let me also take a second to think about this as well. So I know my video here sometimes gets in the way of the actual slides, but let me read the question. So what we have here is a spring mass. Again, it's kind of strange that we're talking about spring masses right now, but just to remind you, what we're doing here is we're modeling each oscillator within this wave as a spring mass. So what we have here is a spring mass which is lifted up and released at 5 centimeters above equilibrium. And then you're told, so that this first piece of information is basically telling you about the amplitude. Then you're told that it takes the mass 4 seconds to complete 12 cycles. So think about what that tells you. Now, if we define time equals to 0, so that has to do with a phase constant. When the spring mass is moving down at equilibrium, the equation describing this spring mass system is. So here are your choices. Think about it. And let's see the answer. All right. So it turns out that there's more than one correct answer here. So let's take a look. So first of all the options here had the amplitude at 5 centimeters, which is what you were given. Now let's think about this equation. So what goes in here is 2 pi over the period. So what is the period? So the question states that it takes 4 seconds to complete 12 cycles. So the period is how much time it takes to complete 1 cycle. So if it takes 4 seconds to complete 12 cycles, so 4 seconds over 12 cycles, that means it's 1/3, 1/3 second per cycle. So the period itself is 1/3. So you have to put 1/3 here, and then if you move that up, we get 6 pi, which is what goes in this part of the sine function. So that eliminates choices A and B, which is, instead of dividing by the period here, it's being divided by the frequency, which is 3 seconds. Okay, so now what we want to think about is the actual phase constant. So let's actually go back a little bit, and this has to do with this phase constant when our starting position was our spring mass at equilibrium and moving down. And what we argued is that the solution for that is pi, because we're shifting our axis, we're starting our wave basically half a cycle later, which is exactly 1 pi. So how come minus pi is always also a correct answer? And that has to do exactly with the fact that you can add any factor of 2 pi, add or subtract to a sine function, and you get the same exact answer. So pi and minus pi are exactly different by a factor of 2 pi. So if we take pi and subtract 2 pi, we get minus pi. So this is just sort of to make a point that there are multiple correct answers for the phase constant. And here kind of show you this property of the sine function. Whenever you add or subtract any multiple of 2 pi, you get back that same value of the sine function. So here n is an integer. All right, so now let's try to kind of combine some things, or our ideas. So far what I have done is I have explained how to mathematically describe one particular oscillator in our medium moving as a function of time. But the entire wave doesn't just describe one oscillator, it describes the whole medium. So remember that also we need to worry about where is each individual oscillator at a given instant of time. So you could think about it, well, we could just have an infinite number of sine functions for each individual oscillator that's describing how it's moving as a function of time. But that's not necessarily a very good solution. Instead, let's try to come up with one function that describes both what's happening as a function of time and as a function of position. So what we will want to do is we want to describe the displacement y of our medium in space and time. Here I want to point out that although these two things are different representations, again, this is the green dot as a function of time, where this is all the oscillators frozen in time at a given time, where I'm defining this as time equals to 0. So here is only one instant of our oscillator here exactly at time equals to 0 when it's at equilibrium. And that point will become important later on. All right, so here is the full wave equation, which you will be working with quite a bit in the next couple of weeks, trying to understand all of its elements. All right, so let's go through this carefully. So now we see that there's two variables. There's position, which describes different oscillators, and then there's time, which describes what each of those oscillators is doing as a function of time. So like with just focusing on one oscillator, we still have these parameters like amplitude, period, and the phase constant, except now the initial conditions are not only at time equals to 0, but also at our origin, x equals to 0, whatever we define our origin. So when t is 0 and x is 0, the phase constant describes our initial displacement. Now this plus or minus has to do with the direction of the wave travel. In other words, if you see if you're an observer looking at a wave, it will have a direction. It's either propagating to the right or the left. And you will cover this a little bit in more detail in DL, the reason behind it. But for now, let's just take it as truth that when the wave is moving to the left, this equation takes a plus sign. When it's moving to the right, it becomes a minus sign. And we will look at a couple of examples later where we'll see how do you determine the direction of the wave by looking at various plots. Okay, and then here is the equilibrium position. So what you see, because it's just a constant that you add to the sine function, all it does is it shifts your sine function either up or down. But in most cases, for simplicity, we will set equilibrium position at 0. But it doesn't have to be 0. Now the new term that shows up here is the term that describes the spatial periodicity of your wave. So that term has a very similar structure as the 2 pi over t times t, except now it's 2 pi over lambda, which is our wavelength, times x, which is a position. So again, wavelength is sort of the spatial period, and it has units of distance like meters, kilometers, centimeters. Now period and wavelength are connected, and they describe the speed of the wave, because what is the speed? Speed is distance over time. So it takes one period for the wave to travel one wavelength. So it's described as wavelength over period. But remember, period and frequency are inversely related. So another way of writing the speed of the wave is wavelength times frequency. So another important quantity is what is known as the total phase of the wave. So the total phase is everything that goes inside these brackets here. And basically what that term tells you, the total phase, is it tells you it's a characteristic of a specific position in your wave. So for example, another word for a maximum versus a minimum, for a maximum we often call that crest, and minimum is trough. So as you watch this wave propagate, this crest will move to the right or the left, and it is described by a specific total phase. So we use capital phi for total phase and lower phi naught for phase constant. So they have two different meanings. Okay, so here's a slide that gives you some important mathematical properties of sine functions. So I've already mentioned this to you, that whenever you add a factor of 2 pi to a sine function, you get the same value back. If you add a factor of pi, where here n is now an odd integer, so let's say pi, 3 pi, 5 pi, that negates the sine function. So you get this negative sign in front. Now, maximum is always described when the total phase is pi over 2. So we get the sine of phi is 1, which is a maximum value it can have. And then the minimum is when it's 3 pi over 2. So you get minus 1. So except for the maximum and the minimum that only has one value of total phase, all other points along the wave will have two values. So for example, at equilibrium, if we go back here, within one cycle, you can have either phi equals to 0 or to pi, so here or here, to give you a value of equilibrium. All right, so I had a little bit of a problem, so I had to stop the video and finish it up a little bit later, but I'm back. So basically what I have done so far in this lecture is summarize the wave equation and all its elements, but what we want to look at next is try to see if it's possible to describe wave motion graphically. So instead of looking at this big abstract equation, can we draw some graphs that help us see how this wave behaves? So one way we can think about it, so remember what this is telling us is the displacement from equilibrium as a function of position and time. So you can think about, okay, well, we can look at every position in space and think about how that position changes as a function of time. In order to make any kind of plot, basically you have to either fix the position and think about how that position changes as a function of time, or fix the time, so take some instant in time and see where are all the positions in our medium are relative to the equilibrium. So you can imagine making a huge number of plots, like for every position, how it changes in time to describe this wave. But what we're going to look at now is actually, we will see that sometimes it is sufficient just to draw two graphs to fully, from which we can extract all the information about the wave. And then from that, we can write down the wave equation for all the other positions and times. So this is kind of our goal here. So our goal here is to look at these two graphs I present here and try to work from here, from these graphs, back to the wave equation and write it down. Okay, so let's focus on what these graphs are representing. So the first one here is displacement as a function of position with the time fixed. So you can always think about this y versus x plots as a snapshot of your wave, because your wave is moving as a function of time. So when you're fixing the time, it's like you're freezing the wave and showing where the medium is, where all the particles or positions in the medium are at that instant in time. So that's why it's often known as a snapshot of the wave. Now this plot here, it's a plot for a specific position in the plate, in the wave or in our medium. So you can imagine now what we're doing is we're looking at one specific oscillator, which happens to be at x equals to 2 meters, and trying to see how that oscillator oscillates as a function of time. So again, this is a snapshot picture, and this is a time dependence of one specific oscillator that we're trying to look at. All right, so what we're gonna do now is step by step look at all these features of the graph to try to figure out all the things that are constant to the graph. So remember, x and t are the variables, but everything else, like the amplitude, the period, the wavelength, the phase constant, and y naught, and the direction are fixed for a specific wave. So what is this y naught? Y naught is the equilibrium position. So if we look at these plots, the equilibrium is right in the middle between the maximum and the minimum displacement, and in both of these, we see that that position is 0. So that's often the most convenient position to choose for equilibrium, just to measure everything relative to 0. So when you go to a maximum, it's plus the amplitude, and when you go to a minimum, it's minus the amplitude. But it doesn't need to be that way, so you can imagine when y naught is not 0, all that does is it takes this wave and it shifts it upward or downward. But in this case, we chose y naught to be 0. Now let's look at the amplitude. So regardless of which of these graphs you're looking at, they're describing the same wave. So the amplitude has to be just the magnitude of the maximum displacement from equilibrium. Whether you're looking up, you get 3 centimeters, or you're looking down, it's also the magnitude of that maximum displacement is 3 centimeters. So we get these two values, which are now filled in. So we put 3 centimeters here, and then find y naught is 0. All right, so now let's look at the period of and the wavelength. How can we get these from the graphs? Well, this first plot here is a function of x. So what it is describing is the spatial periodicity of our wave. So that's related to the wavelength. How do we find the wavelength? All you have to do is measure the length of one cycle. So this blue line here represents one cycle. So we start over here at this equilibrium position at 0.5 meters. You go down, back up, and then back down. That represents one cycle, which ends at 4.5. So the total length or the wavelength of the cycle is 4 meters. We didn't need to choose those 2 points. You could have, for example, gone from this minimum, which is at 1.5, to this minimum, which is at 5.5, and again, would get 4 meters. Now, the period we get from this graph, because this is as a function of time, so it gives us the temporal periodicity of our wave. And here again, I'm choosing this equilibrium point to this equilibrium point to represent one cycle. So we go from 2 and a little bit to 8 and a little bit, and we find that the period is 6 seconds. Also, although we don't need to know the speed of the wave in order to write down the wave equation, in case you wanted to know it, you can now calculate it quickly just by knowing the period and the wavelength, because the speed of the wave is just the wavelength divided by the period. 4 over 6 seconds gives you 2/3 meters per second squared, and this is how fast our wave is moving. All right, so the trickiest thing often with these plots is trying to figure out the direction. So remember, this plus or minus sign had to do with which direction the wave is moving. This wave, remember, it's frozen at time equals to 0. So the question is, at a later time, will this peak here, this crest, is it going to move to the right or to the left? If it goes to the right, we write down a minus sign. If it goes to the left, we write down a plus sign. So how do we think about this from these waves? So the first step in thinking about it is to find a connection between these 2 plots, or in other words, the common point. Because these 2 plots are representing 2 different things. This is all the oscillators at a given time, and this is all the times for specific oscillator. There's really only one possible point that can connect these 2 plots. So because this is representing time equals to 0, that's exactly this point right here. That's this oscillator, which is at 2 meters at time equals to 0. Now we have to go to this plot and find that oscillator. That's at 2 meters. So it's right here. So you could see, of course, these 2 plots have to be consistent. So that oscillator at 2 meters and 0 seconds has to have the same displacement, and that's true. As we see, it's about minus 2 meters. So, okay, so how does this help us figure out the direction? So if we focus for a second on this plot, what we see is that at some later time after 0, which is not given here, but what we see here at some later time, this displacement is going to go towards a minimum or towards a trough. So that's kind of represented here. At a later time, it's going down. So now what we want to think about is, in your mind, turn on this wave moving, or unpause this movie, and think about it moving either right or left. So let's take a guess. Let's say the wave is going to move left. So what's going to happen? If this wave moves left, then what's approaching this oscillator is a crest. So what that means is that at some later time after 0 seconds, the displacement is going to move up rather than down. But remember, we just concluded from this plot, which tells us that the displacement has to go down. So in other words, this is not consistent. So it is not possible that the wave is moving to the left. Now let's look at the other case where the wave is moving to the right. So if it is moving to the right, what you're picturing is that you're shifting this wave. So it is indeed a trough that's approaching this position at 2 meters, and the displacement is going down. So indeed, we found that the wave is moving to the right. So we put a minus sign here. So another way of seeing it is, so we were kind of picturing in our head this movie turning on, but let's just draw it. So with the wave moving to the right, So this is our original wave of at 0 seconds. So imagine then it shifts to the right, and in about half a second, it's gonna be exactly there. So the dashed plot is sort of the future of this wave in half a second. So what you see if you look at 2 meters, what this tells us is that at half a second now the displacement is lower or farther away from equilibrium than it was at 0 seconds. And if you look at this plot, that's exactly what this plot is telling us, is that at half a second is going to be over here. So again, this is consistent with shifting this wave to the right. If we shifted it to the left, we would get the inconsistent result. All right. So you will practice this quite a bit in DL, and some of your F&Ts kind of thinking about the wave direction, but that's often the trickiest thing to visualize when trying to write down this wave equation from the plots. All right, so now that we got everything, the only thing left to think about is this phase constant. So how do we think about that? Well, the best way to figure this out is find some values of x and t where we know the displacement. So if we can basically write down a number here, then we can solve for phi naught. But we have to be a little bit careful, because if we find, for example, an equilibrium point, there's more than one answer for that. For every point, there's more than one answer. For example, sine of 0 and sine of pi gives you a 0. So for this to not be ambiguous, it is best to always choose either maximum or minimal point to work with, because we know that, for example, if we found a maximum point, it's only sine of pi over 2, and that gives us that value. So that's exactly what we're gonna do. So I happen to choose this point here, and what do we see here? Well, we know that the sine to get basically 3 meters, which is the displacement at this point, then the sine of everything inside has to be 1. How do we get the sine of the argument to be 1? Is that argument has to be pi over 2. So in other words, and this should be y, not phi, I'll fix that. So basically the displacement y at 0 seconds and at 3.5 meters, which is exactly the location of this maximum, is equal to pi over 2. So what we have to do is take everything that's inside these brackets and set it equal to pi over 2 at these two values. So let's do that. So again, we're taking our wave equation, and now for t, we plug in 0. For x, we plug in 3.5 meters. And again, this should be y, not capital phi. Capital phi is the actual phase constant, which is what's inside the brackets. So everything then inside the brackets has to be set equal to pi over 2, because we know that sine of pi over 2 is 1, because we chose a maximum point. So then you manipulate the algebra here, and then what's left is to solve for phi naught. And if you move this to the right side of the equation, it ends up being 9 pi over 4. So I'll leave it up to you to work through that math. But, you know, this number is kind of not so pretty, so it's often nicer to represent your phase constant by a number which is closer to 0. So remember, we've already discussed that you can put you can add or subtract any multiple of 2 pi inside the sine function, and you get back the same exact sine function. So if we take this 9 pi over 4 and subtract 2 pi, which is 8 pi over 4, you get exactly pi over 4, which is kind of a nicer number to think about compared to 9 pi over 4. So one thing that I wanted to point out is that we didn't need to choose this point, maximum. Let's say you could have chosen this minimum to work with. So at time equals to 0 and x is 1.5, we see that the displacement is -3. When is the sign of something equals to -1 is when it's not pi over 2, but 3 pi over 2. So if you chose this point to work with, and then you set everything inside to 3 pi over 2, you should get exactly the same phase constant. So there's nothing again special about choosing this, or you could have chosen this point or that point and worked through the math. So this is what I suggest, is for you to try to use another point and make sure you arrive at the same result. All right, so now we're officially done, and we can write down our now full complete wave equation. There should be an x comma t because there's two variables. There's the time and the position. So again, I'll fix that when I post the slides, but it won't be fixed in the recording. All right, so I think I have some questions, and again, this is not a live lecture, so I'm not asking you clickers. Let me move my video a little bit out of the way so you can see, but I suggest that once you read the question and hear me describe it, you pause the video, think about it, and then continue when I explain the answer. All right, so what do we have here? A wave is propagating to the left with a period of 12 seconds and a wavelength of 8 meters. At some instant of time, there's a crest which happens to be at 10 meters. So where will this crest be in 3 seconds from this time? All right, so think about it. Let me think about it as well. All right, so one thing I noticed, or I can already think about, because the wave is moving to the left and we're talking about a particular crest at some instance of time, and I'm asking about where's this crest going to be later. If it's going to the left, it has to be a value of x which is smaller than 10 because it's going towards decreasing axis. So it cannot be D or E, it has to be A, B, or C. So now the question is, how much does the wave move in 3 seconds? Well, we know that in 12 seconds, it moves 8 meters because that's exactly the definition of period, is how long does a wave move one wavelength. So if in 12 seconds, the wave moves by 8 meters, then in 3 seconds, which is 1/4 of the period, it will move by 1/4 of the wavelength. So 1/4 of the wavelength is 2 meters. And again, because it's moving to the left, it has to go to decreasing x, so it's gonna end up at 8 meters after the 3 seconds. Okay, so here's another question where now I want you to think about how to figure out the direction of the wave motion. It's just try to follow that same identical procedure that I described in the example. First find the common point, then try to shift the snapshot plot to see which way your oscillator should be going. All right, so let's think about this. I have to keep on moving my video to not block the slides. Okay. So remember the first step, well, here actually, so write down some things of the wave equation. We look at the of time. It looks like one period, yeah, it's 4 seconds from 1 to 5, and the wavelength, it's about from 1/2 to 3.5, so 3 meters. But that's really not part of the question. All you're really asked to think about here is direction. So what is the common point? So here we have y versus x at 2 seconds. So that's 2 seconds is over here in this plot. And this is at 2 meters, and 2 meters is over here in this plot. So in this case, this is our common point. So this is kind of an interesting example because this wave is describing a common point which is sitting at a trough. So imagine if we have an oscillator which is currently at a trough, whether the wave is coming towards the oscillator from the right or the left, there's only one way for that oscillator to go, which is up towards equilibrium. So basically, if you took your snapshot plot, which is over here, and whether you shifted it, so basically this plot is telling us that at some later time, the oscillator is moving up. So if you took this plot and you shifted it to the left, it's going up. If you shifted it to the right, it's also going up. So in other words, if your common point is either a trough or a crest, because when you're at a crest, again, the only way you can move is down, regardless of which direction your wave is moving. This is kind of one ambiguous point, data point that you can have on these two plots, which actually does not tell you the direction directly. So this is just not a good choice of the two plots to give you direction. So you cannot figure it out from these two. But in any other scenario, when the common point is anything other than a crest or trough, then you could use that argument of shifting the wave to figure out which way the wave is moving. All right, so it was a bit of a tricky example. Okay, so the last topic that I will cover in today's lecture is known as the Doppler effect. So far when I have been describing the wave and the wave equation and characterizing things like period and wavelength, I've been thinking about a source. A source is, again, something which is creating your wave as stationary. So the actual source itself is not moving. The only thing that's moving is the wave. Likewise, if we're talking about an observer, so someone interpreting the wavelength and the period of that wave. So for example, if I'm talking and you're standing in the room, you're the observer. So the source, which is me, whatever pitch of sound I reproduce, you hear that same pitch. So this is true, though, it turns out only if the source and the observer are not moving relative to each other. But rather they're stationary. But now we're going to look at what happens to our interpretation of these properties of the wave when either the source or the observer are actually moving. All right, so here's an example. So another way that sometimes we represent waves, and instead of writing down the wave equation or making these plots as a function of time, or as a function of space, is we draw these circles around the source. So our ambulance is the source. We're drawing these circles that basically just represent crests. Because the sound, it's emanating everywhere in 3D space. Actually, they should be spheres, but because it's a two-dimensional picture, all you see is circles. And then the distance between these two lines will represent one wavelength, because these are two neighboring crests. So what we see here is an ambulance which is moving, and it's moving towards this observer. So basically what happens is, when the ambulance is stationary, it emits a specific a siren with a specific frequency, which means that it's emitting a crest of the wave every specific time determined by the period of the wave. But if the ambulance is moving, by the time it's ready to emit, let's say, a second crest, the source itself has moved, so it's going to emit a crest in such a way that it's going to be already closer to the next one. So the wavelength, or the distance between these neighboring waves, will decrease. If the wavelength decreases, it tells you that the frequency increases. Remember, they're inversely proportional to each other because the speed of the wave is frequency times wavelength. So wavelength goes down, frequency goes up. Now the opposite happens. So basically, if you're an observer standing in front of the ambulance as the ambulance is approaching you, what you're going to hear is a frequency which is higher than the actual frequency emitted by the ambulance when it's stationary. Now, if you are an observer behind the ambulance, the opposite effect happens, because the ambulance emits a crest, then it actually moves a bit before it emits a second crest, so that stretches the distance between neighboring crests. In other words, it makes the wavelength longer wavelength, lambda goes up, frequency goes down, so the frequency is lower. So if you ever wondered why is it, and sometimes you're standing on the side of the road and an ambulance rushes by you, the pitch of the siren of the ambulance sounds different. So if you thought it has something to do with actual pitch changing, that's actually not it. It's this Doppler effect itself that's doing it. So as the ambulance approaches you, you kind of should hear more of a high pitch sound, high frequency. As it recedes from you, the frequency or the pitch should become lower. So next time you hear some emergency vehicle rush by, you pay attention to this. So this is exactly what is known as the Doppler effect, this apparent change of the frequency of sound when there's motion involved. So there is this pretty involved formula here, which you're going to work with in DL, that basically connects the frequency of the source that's being emitted to the frequency that the observer observes, depending on the relative speeds of the observer and the source. So in this ambulance example I showed you here, it's only the source that's moving, but you can imagine that if the observer itself was moving as well, then that would also have the effect of changing frequency. Okay, so let's just look at some of these terms. So V here, that's the speed of the wave itself. So in the case of an ambulance, this example we've been talking about, that's going to be the speed of sound. V naught is the speed of the observer, and Vs is the speed of the source. And then these plus or minuses, you choose those depending on the direction, the relative direction of travel. So for example, in the numerator here, plus is when the observer is moving towards the source, and minus is when observer is moving away from the source, and then so on. So let's kind of look at our ambulance example and think about how to simplify this to fit that example. So let's imagine our source, which is the ambulance, is moving now towards the observer. So we're thinking about the observer that's standing on the right. So if we look back at that equation, the observer himself is not moving, so that speed is 0, but the source is moving, and the source, so that's the denominator, is moving towards the observer, so we should get a minus sign. So that's why we choose a minus sign. So if we look at this equation, the quantity in the numerator is bigger than the quantity in the denominator, so the whole ratio is going to be bigger than 1. So what we find is that the frequency of the observer will be larger than the frequency of the source. And if we kind of look back at this picture, again, that's exactly what we get. So when the source is moving towards the observer, the frequency increases. Now, this is kind of an interesting example where imagine both the source and the observer are moving, but they're moving together with the same speed. So in other words, the source is moving towards the observer while the observer is moving away from the source in the same speed. So what you see when that happens, the distance, the relative distance between the source and the observer doesn't change. So in fact, nothing should change. The apparent frequency shouldn't change either. And that's exactly what we get. So if we look back at this equation, back to the previous slide, we should find that when the source is moving, when the observer is moving away from the source, that should be a minus sign. So that's a minus sign here. And when the source is moving towards the observer, in the denominator, again, a minus sign. And now what I'm saying is let's set V naught and Vs equal to each other. So if they're equal, then this ratio just becomes 1 and the two frequencies are equal. So what you're going to do in DL and some FNTs and practice problems I will post, you will kind of get a better sense of this equation by trying to practice it with it and see what happens when, either the source is moving, the observer is moving, or both are moving relative to each other. Okay, so I have kind of a clicker question that hopefully can give you a little bit more of an intuitive understanding of Doppler effect. So it's sort of an analogous situation. So imagine that during peak hours, a train is traveling in each direction on the Metro Gold line in Los Angeles, and each train arrives at a train station at a consistent frequency of 6 minutes. So every 6 minutes, there is a train arriving. So for example, if you're standing on the westbound track, you see the red train. In 6 minutes, you will see the blue train. But now imagine that you are actually on board during peak hours and you're traveling westbound. So you're actually sitting in this yellow train which is traveling. And the question is, how often do you pass a train which is headed in the opposite direction? So think about this. All right, so the answer is, if you think about this, so again, if you are stationary on the west track, what would happen? You know, once this red train leaves, in 6 minutes, you see a blue train. So you see one train every 6 minutes. But if you're traveling yourself with that same period, which means that in the 6 minutes that it took the blue train to get here, you in the yellow train are over here, and that's exactly how much time it would take for the green train to get to that position. So in those 6 minutes, you saw 2 new trains. In other words, what you're seeing is a train every 3 minutes. So you're seeing the trains with double the frequency. So how can we actually use the Doppler equation to try to understand the scenario? So, you know, Doppler equation only applies to waves. So it's not, you know, these trains are not waves, but it's just an analogy. So you can think about the eastbound track as sort of your source, which is emitting a wave. It's not a wave, it's a train. So it's kind of spitting out these trains every 6 minutes. So that would be the frequency of the source. Now the observer is you in this yellow train moving, and you're moving with the same speed as the source is moving, because you're moving in such a way that you move this given distance every 6 minutes. So the speed of the source, again, the eastbound trains, is the same as the speed of the observer. It's a plus sign because you're moving towards the source, or in other words, in the opposite direction in which the source is moving. So that's a plus sign. The source itself is not moving. If it was moving, then these trains would be sort of getting closer and closer together. So imagine there's just some source which is saying, okay, train, come out in next 6 minutes at the same location the next train leaves. All right, so if you do the math, what you get is that this gives you a factor of 2. So indeed, what you find is that the frequency of the observer is double the frequency of the source. So if the frequency of the source is every 6 minutes, then the frequency of the observer becomes every 3 minutes. It's the period is half, but the frequency is double. All right, so I think this is kind of a very illustrative example that helps you think about what's happening when there's a Doppler effect. All right, so finally, I just want to give you a couple of applications of Doppler effect. You know, it seems like a pretty abstract idea, but in fact, it comes up quite a bit. So if you ever wondered how a police officer sitting in their car on the side of the highway knows exactly the speed at which you're going by pointing this radar gun at you. And this radar gun actually works exactly with using the physics behind the Doppler effect. So it's not like the police officer sitting there calculating things, but this radar gun has this built in. So imagine when the radar gun is shot, it's set to emit waves or radiation at a very specific frequency. And if it's pointed to some car which is approaching, basically every crest that hits the car is going to bounce back and go back to be detected in the police car. So if the car is approaching, then by the time one crest bounced back, the next crest that's going to bounce back, the car has had time to move, so the wavelength is going to get shorter of the wave that's reflected off it, and shorter wavelength gives you higher frequency. And as you saw from the previous equation, knowing this difference in the frequency between the transmitted wave and the reflected will give you exactly the speed of the car. So the opposite is true. You can use this radar gun to figure out the speed of a car, which is receding, which normally is actually what's done, because police cars do not drive on the other side of the highway to catch speeders. So normally they will look at a car that has passed them and is receding. So the same idea, except now the reflected waves will have longer wavelengths, so lower frequency, and again, that frequency can be converted to the speed of the car. So another more almost cooler example of Doppler effect application is, this was sort of the first way that we explained why our universe is expanding. So how did we know that? Well, there are certain stars out there in the universe that have known type of radiation that they emit, or electromagnetic radiation based on the type of the star. We know what kind of wavelengths and frequencies they should emit, but what was found is that no matter where in the sky people looked around the Earth, they found that those wavelengths that came from those stars were longer than expected, and this is known as redshift, because red light or red wavelengths are longer than blue one, for example. So this is sort of, let's say, what would be the expected emission, but this is what we saw. So what does that tell us? How can we get longer wavelengths? So if the star, let's look at this car, imagine now it's a star. If it was moving away from the observer, then the wavelength that we would observe would be longer than the actual wavelength emitted by the source. So, and because we saw this effect, this redshift anywhere in the sky, the conclusion is that as you look around, everything is receding away from us. And how can we explain that? With the fact that indeed the universe is expanding, growing larger, and things are moving away from each other. So this is kind of a very cool example of Doppler effect. So there's also an application in biology, and specifically ultrasound imaging. The Doppler effect, for these same kind of arguments that's used in radar and explaining the expansion of the universe, is used to detect or to calculate the speed of blood flow. So the same way as the radar gun was shooting wavelengths at a car and then picking up the reflected wave, which told us how fast it was moving, an ultrasound emits sound waves. So ultrasound is sound waves. Then bounce from some, let's say, blood that's flowing, and depending on the speed of that blood flow, then the reflected frequency is going to be different. So knowing the received Doppler frequency compared to the transmitted, we can figure out the speed of blood. So why could that be important? Well, for example, if you have an aneurysm, which causes a different speed than normal, as we saw back in 7b, remember the pressure goes up, or area goes up, means speed goes down. So if you see a slowdown in blood flow, that could be a clue that there's aneurysm. Or if there's a blood clot and blood is not flowing there, so you're seeing blood flow which is much slower than expected, that could give you a clue that something is going on. All right, so I think that's it for today's lecture. I hope you enjoy it, and I will see you again soon.